Hi, I'm Cliff. Okay, I want to talk about big data. I guess the first thing to do is qualify with people what big is, because everyone has a different notion of big. So I guess I'll open up by asking a question here. So how many people here work with big data? So, like 2. So what do the rest of y'all do? Why are you in this talk? So how many people here, let's try again here. How many people here work with data sets that are typically a gigabyte or larger in size? Oh, okay, fine. Okay, how many people work with 10 gig data sets and larger? Okay, 100 gig, terabyte and larger. Now we're getting down to, okay, how about 10 terabytes? Let's see, 100 terabytes. Okay, now you're getting up to what I would call big, so petabyte. Right, and on up. All right, I'll stop here. So there's a couple guys go all the way up to petabytes, and then there's probably Google people who will keep going to exabytes. So for what we're doing, big. Well, that was very exciting. Let's try again. There we go. Big is somewhere between gigabytes and terabytes, in the sense that beyond terabytes, that's too big for an in-memory solution conveniently. So we're building a platform. It's pure Java, open source. You can get it straight off GitHub, and the website has got a jar file that you can download and go. It just takes one jar, and it often runs. And it's doing, it's a platform for doing parallel distributed math. And then, given a platform for parallel distributed math, what does that mean? Well, besides being able to do sort of any kind of generic math you want, we're building high-end math, machine learning algorithms, logistic regression, generalized linear modeling, gradient boosted method, random forest, deep learning, neural nets, on and on and on, a bunch of stuff. So I guess I'll go hand in hand with that. So how many people here are using machine learning at all, or looking at it, or thinking about doing anything with machine learning? Okay, some amount. And how many people are using machine learning on sort of a daily basis now? Like you're sitting at your desk and you're building models on a regular basis. So and anybody here have plans to go there where you're going to build these models and try to apply them in production? So a couple of people. So people are out there making their plans. Okay, so this talk is actually, I'm not going to go deep into machine learning algorithms and the math side. I'm going to talk about building a systems platform for allowing machine learning algorithms to be built. Okay, so I said this is a platform for doing big data work. So what does that mean? In this context, it means almost any Java you want on a big two-dimensional table. So anything that reads or writes a single observation in your data set, a single row, plus maybe some nearby rows, and maybe computes a reduction or produces a big data output. Within that constraint, the speed is interesting because it's big, and the speed is typically data volume divided by your memory bandwidth. It's limited by memory bandwidth frequently, which is like 50 gigabytes a second per node. And it varies by hardware and by your original setup, and some of the algorithms require more network traffic, and so maybe that's the bottleneck instead of memory bandwidth. But we typically see numbers that are 1,000 times faster than anything you can do on a Hadoop. It's a pretty low bar, but we're still seeing numbers that are 10 times faster than anyone else on the planet. It's really fast stuff. So that opens up the door to doing interesting things. I mentioned the data is compressed. I'll talk more about that later. It's typically much better compressed than what you get from like gzip on disk, and that goes straight to the memory bandwidth data volume trade-off for speed in the good direction. I'm doing math, so I'm limited to data that is math-like. Numbers and times and simple strings. And then I said two-dimensional table. How big is the table? Tables that are less than 1,000 columns wide are going to be really fast, like too fast that you can hardly care. Up to 10,000 columns works still fairly well, and 100,000 or bigger still works, but the loops are parallelized the wrong way, and it's not as fast as maybe you'd like. But the length of the table is limited memory and can be millions to billions to trillions long. It can be very, very, very long. So more or less, a couple terabytes of cluster will turn into, tens of billions, hundreds of billions of rows, and that's fine, and it will all go fast. Okay, so what can you do with it? So I'm going to step through some examples here from a developer point of view. And the most common thing we do is a MapReduce paradigm. And it's not the only paradigm we support, but it's the common one because it scales out just completely nicely. So a MapReduce will take something of a type A in the map call and produce something of a type B. In this case, it's double to double, and I'm just computing a square. And then a reduction will take two of the B types and make one. And here I'm doing a simple add. And so this is just sum of squares. And I write this Java code exactly like this, and I say do all on my data, and it's going to run at memory bandwidth speeds. So this will take a terabyte in under a second, in some tens, hundreds of millis, depends on how big your cluster is, just like that. So I have a Scala version in development. It's still being whacked on. It's not 100% complete, but it's clearly about half the lines of code, and you can get the notion really quick that you're just doing sums of squares here. So it's kind of a slick thing. So I said before, I have as a map and reduce. The map is from a type A to a type B, where the type A is your big data. It's your input. It's however many columns you've selected out or how many thousands and hundreds of thousands of columns you have. That's your type A. And you can treat it as a struct, if you will, but it's an array of structs versus struct of arrays. The two notions are sort of interchangeable here. A is your big data, but row by row by row. And your type B is your output. And there's two types of output. There's big and small. Big data has to go right back into the cluster because by definition, the big is too big to fit on one node. So if you have a big output that is on the order of magnitude of your original input, it's going to be a distributed output. It's going to live in the cluster's memory the same way as your input is. You can also have a small data output, which is a plain old Java object. And the reduction will take two such POJOs and produce one. I'll do update in place where possible. And ultimately, you simply make a new instance of a MapReduce task, override MapReduce, and say do all, and your original instance comes back with whatever your reduction was asking for right back in that instance after it's visited your terabyte of data. So here's some examples of that. Here my type A is a double pair x and y, and my type B is the this pointer, an instance of linear regression past 1, which is computing sums and sums of squares again. And you can see it's simply adding directly into the Java object and calling reduction takes a this and a that, which are two of the same type thing, and folds them together. There's a Scala version. It's about half the lines of code, a little uglier on a slide. But when I say it goes right back into the original object, I made a foo object, and I can directly use it in the next line of code to go compute things straight off of foo. And then usually that feeds into the next pass. I just write the next piece. In this case of linear regression, there's 3 passes, and you would say pass 1, do all, pass 2, do all, pass 3, do all, a little bit of algebra in and around the passes, and it's a done deal. So there's an efficiency thing here, and to get my memory bandwidth speeds out, I have to actually dodge all kinds of overheads. So under the hood, whenever I say map, there's actually a for loop that's running over some chunk of data. I'll get more into what a chunk is here in a minute, but it's some collection of 1,000 to 1,000,000 of your elements that one core is going to do something with. And there's a simple for loop that you can write yourself, or you can let the system throw in for you over your own map call. The chunk at, cx at, cxy, that's the decompression step. Talk some more about that in a minute because it counts for speed so much. And then you do your standard map and reduction the way I showed it a minute ago, and those are all just the same. Because you have a for loop here, if you have interesting, complicated map functions, you can haul loop invariants out yourself. If the JIT's not going to do that for you, you can do it yourself. And when we do our own internal math algorithms, we will often have map functions, which are 1,000 lines or more of Java code, and we'll be doing a lot of sort of manual optimizations to haul loop invariants out and things like that. Okay, so here's another quick kind of thing I can do. I'm going to count somebody instead of compute a math, and this is just a filter. If your input data passes some particular filtering condition, count as a 1 or a 0, and the reductions add them up. And the Scala syntax is again a little bit, it's a lot shorter and a little bit cleaner. And I'll get counts that way, sort of however long it takes to shove the data through the memory bus. In addition to doing counts, I can also collect sets, and this is a big data output, where I've made a new output vector, and I've said do all, passing in my inputs and my outputs, and then I can use it immediately in the next step. And somewhere in the body of the map call, I've picked some condition, and then set append, and that collected an output set that's too big to fit on one machine typically. You know, whatever the percentage of people who passed the filter, they got shoved into the output set. But I might have an output set that's a terabyte in size. And if I'm filtering hugely, maybe it's small, but if it's big, it's going to be too big to fit on one machine. So the output just has to be distributed. So this is a little bit more about the coding style. Here's basically a group by, where I'm going to ask a question. How many cars do people own at different ages in their life? And the more interesting thing here is I've done an allocation in the map call. And the key trick with that is it's a private allocation. It's privately done by one core. It's single-threaded access. So in particular, that ++ out in the end, it doesn't have to be synchronized. This is one core doing one piece of work, and there's no synchronization involved. But then every core is running on a different chunk of the data, and so you have a whole lots of these little car ages arrays. So you have to have a reduction to roll them up. And I have a little utility that's going to help just do, you know, array element add there. Here's uniques. In this case, the difference is I've done a new in the constructor instead of in the map call. And that meant at the time I called new uniques right here, I made an instance of an object. And when I said do all, that object got replicated around the cluster with everyone sharing as much as possible of the one instance I just made. That's very useful for read-only sets. But if it's writable, then you have to handle concurrency. In this case, it's a non-blocking, it's a concurrent safe hash set. So I can have everyone just write in. So the map function simply jams something into the hash set where the hash set's going to filter for dupes, and the reduction moves things together, and that's called whenever I have to move these hash sets across the wire. But in so many lines of code, I can compute uniques in my data set across the cluster. Okay, so that was sort of the quick whirlwind tour. I'm going to summarize the limitations here, and the main one is, you know, I can't do any machine level resource allocation because that won't be cluster wide. So no I/O. In particular, every member of the cluster might have a different file system view, so you can't read or write files sort of meaningfully there. So no new threads, no locks. There's no distributed locks here. No calling system exit. You don't have any global variables per se. Instead, any global or static variable becomes node local. Now, if you actually need global state, then if it's readable, you put it in the constructor, and it'll be cloned around as a read-only thing for every member of the cluster, every thread to use. And if it's writable, you're going to have to use a reduction call to get the results to roll back up and come back to you as a truly global written result. And for the big state, you just read and write straight into the big data. Same as you saw reading, you can write to it as well. And the typical paradigm here is you're going to run in one MapReduce step, and then do a little bit of algebra, and then run another one, and another, and another. Where the key here is that the typical time to do a tire pass of the data is in the modest number of milliseconds. So it's a different story than your typical, you know, MapReduce paradigm. Okay, the strengths here is that the code's running sort of distributed in parallel without any more effort. And the code I was showing here, it actually works just as written. You just say, you know, new MapReduce task, override MapReduce, bang, done. You can write in a single-threaded coding style, so you don't have to. There's no synchronization, and there's no talking to the cluster mechanics somehow to do whatever setup. There's no concurrency issues. There's no resource management knobs you have to turn. Once the cluster's up and running, you know, all your maps and reductions just do the right thing immediately. There's no knobs needed for GC or CPUs or network or data placement. There's no hot blocks or hot locks. You know, that's all taken care of under the hood, and actually it works really well. Okay, so that was like the whirlwind tour of what I can do with it here. Let me stop and see if anyone has any questions about what I just said. Yeah.
So does H2 run on static datasets, or can I kind of feed data into this dataset live?
So right now we're running on static datasets, where one of the first steps to do is load data. That said, the core architectures totally support streaming, and we just hadn't had enough users asking for it to put streaming down. So we add algorithms and features based on what we have customers pay for, and as soon as you get a quorum of people who said I'll pay for streaming, then we put it in. It's getting there. Streaming will probably be here before the year, before next year. You know, a year from now, we'll have the streaming support in there. Okay, so let's take a look at how it actually works. This is an instance of fork join, but I want to say distributed fork join. So it's similar to Doug Lee's fork join work. I'm actually using his fork join work sort of directly within a node, and I've extended it to work cross node. And the way you look, here's an 8-node cluster. Somebody somewhere is driving this and has said, make me a new MapReduce task and do all on some data. And then I do the sort of obvious log tree fan out where I pipe the instance of this object after the constructors run. It's all set up to his 2 neighbors, and they send it to their 2 neighbors, and so on, until the whole cluster has got an instance of this task. Now, as soon as the task hits a node, it also goes on the fork joining work queues, and then they do what fork join's been doing all along, which they start making clones of themselves as long as the data set they're referring to is too large, and they do a divide and conquer, and they split and make another task, and so on, until the amount of work assigned to an individual task corresponds to one chunk of data, and then they all do parallel map calls across the data. And fork join's really good at doing load balancing and sort of on the work on the data. So this will slam all the cores on the box. You'll go 100% CPU load, they'll all do their thing, and then when they're done, each of the objects will have the small data POJOs left in the task objects, the clones of the task objects that have been made all along. And then there's a reduction step, starts going in reverse, where pair by pair, as soon as 2 guys have completed their mapping steps, you do an immediate reduction in place, and then those log tree roll up and make another reduction until you get with a single top-level instance per node. And then you run the cluster-wide log tree in reverse, going backwards, where the poor fellow at the long end of the log tree on the right reduces up to his 1 friend, and the other 2 guys are going to reduce to their friend that they got their task from. And then in the next step, the reductions continue back through the cluster until you come down with the final reduction into the original instance, and it's done. So the time to run this is typically log tree fan out through the cluster, parallel execute on the nodes, log tree fan in from the cluster. And that turns into some, count of milliseconds depending on how complicated your maps and reductions are. Okay, so it's pretty straightforward. Nod, maybe some, okay, fine. So let's look at the data layout. So this is an interesting problem because people, seem to sweat a lot about data placement, data layout. And we were sort of doing something that's very straightforward and has been working quite well in practice. So the abstract API is that I have a collection of vectors for my data. That's the 2-dimensional table thing, where a vector is 1 column. And the column is treated like an array, but it can be longer than an int in length. It can be billions of elements in length, right? And there's fast random access to any given element, although if one node asks for all elements, he'll get drowned in the data. It's too much, right? But he can pick individual elements for free. There's a notion of the missing value. That's an is and a. It's very key to the machine learning math algorithms to have a notion of missing. Your algorithms do something different on that. And you can write it or append, so you can muck with the size of the data sets or change them in place. It's all fine. So like I said, I have a single large vector. Conceptually, it's full of typically Java primitives. However, that's the conceptual view. It's actually compression is whatever it's going to be. And it's all geared for fast linear access. It's striped across a cluster. So here I have a 4-node cluster I'm showing. Chunks of the data will be on every member of the cluster. So it's not striped with one vector holding, one JVM holding whole vector. Instead, it's distributed across the vector. And it is fully in the Java heap. So the data is actually in the Java heap. And we do a lot of work with GC to watch the size of the heap, and we build a disk on demand and do a bunch of stuff there. But the end result is if you take the default collector and you set it as large as you want, we'll not have a GC problem. We don't see, we routinely run with 250 gig GC, XMX 250 gigs on a 256 gig machine with max GC pauses in 1 to 2 seconds every now and then. You don't get these giant GC pauses. Okay, so I said I had a vector. Typically, I actually have a bunch of them, and they're all aligned. And they're aligned this way so that one core on one JVM can access all members of a set of an observation going across at memory speeds. So while you can get at the data with random access on any row, any JVM, you're fastest if you're doing it in sort of one core going across on a row. And the reason it's set up like this, of course, is that your data sets represent some real-world feature set. And here I'm showing age, sex, zip code, ID, car, whatever it's going to be. And conceptually, this is an array of structs or a struct of array model, and you flip back and forth in your head which way you want to view it, and I can hand the data to you in either way. similar to an R data frame. So we can add or subtract columns sort of for free. It's like a pointer change to do that. So a common setup is to collect in however many 1,000 columns you have and then decide what columns you're going to work with. And you probably drop a bunch of columns out, and then you probably filter and hack on a bunch of columns to build out more features, and then you'd pass it on to the heavyweight math algos. But all the adding and dropping of columns is all sort of for free. Okay, within a column, there's this thing called a chunk I'd mentioned earlier. It's just the unit of parallel access. A chunk is typically 1,000 to 1,000,000 elements in size. It's stored in byte arrays in the Java heap, so plain old byte arrays. And it's where we do compression, and we vary the compression strategy by the kind of data we're observing in that chunk. But the guarantee is that get or put of any given element is just a few clock cycles, including the compression step. In this case, the compression is one of the key fun things we do for speed because we're moving the compressed data through the memory hierarchy and decompressing it in machine registers on the fly. It's sort of completely free to decompress because we can't pull data in fast enough anyhow. We're all blocked behind the memory bus. So more compression is actually better. And then, of course, every a row across is sort of owned by a single core at a given point in time. So that core can access every member of the row, like he's single-threaded, like he has a Java object. In fact, I'll just build you a Java object if you want one. And then, he can just scribble at it at full Java speeds. So it's his private data structure that he can just mangle as he wants. And then I said that single-threaded on that set of rows. There's enough chunk work there to cover the cost of launching enough threads to get everything busy, but that's small enough that I get good fine-grained data parallelism. So it's this sort of good blend of just big enough to cover the cost of launching more threads, just small enough to get good parallelism. And so, of course, what really happens is every core lights up all in parallel all at once. Yeah. How do I make sure the data is aligned? I load it that way. So when I inhale the data sets, I will start selecting what rows are going to go on what machine across the data. So a common thing to do is read in a terabyte CSV file. So CSV means it's variable length on every row. It's all kind of mishmashed up. And I'll parse through that and build my compressed format and then make a decision about what rows are going to go in what places. And I'll group them together, but I'll carefully arrange them all node by node by node that you have a compatible set of rows across on a single node. And then there'll be one network shuffle. So you load a terabyte in, it came from disk. So the network is 1,000 times faster than disk. So the network shuffle's essentially free now, and you're limited by disk speeds, right? So to get the data in. So I'll do one shuffle under the hood to get the data where I want it, and then it doesn't move again. Okay, so there's a quick summary. A data frame is a collection of vectors. It's really a distributed data frame. It's all the data throughout the whole cluster. And then the vectors are themselves a collection of these chunks, which is my unit of parallel access. A chunk is 1,000 to 1,000,000 elements. It kind of varies according to all kinds of funny factors. And then an element's conceptually Java double, although it's actually how it's represented under the hood varies by compression strategy. And like I said, I have like 15 different compression strategies that I use right now. And then a single row is a single sort of observation or instance or conceptually a Java struct of those columns. Those are things that you manipulate directly in your map calls. Okay, so is there any more questions on this step? Bam. Okay, so let me break for a second and do a demo, and then I'll come back around to a few other odds and ends, and that's actually most of the talk. So let's see if I can get a demo going here. So somewhere in the world, I'm going to launch java-jar xmx. Okay, my cluster came up. It's a cluster of one on my laptop here. Let me get this going. So I didn't talk anything about deployment, but it's a standard single jar file. So it runs fine on my laptop, and I can cluster up on my laptop by saying java-jar, ampersand in the background, run it 2 or 3 times, and get a cluster of however many I want on my laptop. It'll run in the cloud, run in EC2. It'll run on your own private cluster. It'll run on Hadoop. It'll run not on Hadoop. It'll read from HDFS or S3 or wherever. Because it's a simple jar file, you can just go pretty much anywhere with it. So I'm going to start by loading a data set here. I'm going to pick, what do we got here? Data sets. Let's pick the nice UCI. So we're going to pick a thing called cover type, which is a forest cover type. It's a pretty old data set that people use in machine learning a lot as a demonstration data set. I'm parsing a CSV file. I'm going to see the breakout of the initial lines. So the data set is about 75 megabytes on disk. As you can see, if you read up there, it's about 500,000 rows, 55 columns, about 10 megabytes in RAM. That's the compression ratio between disk and RAM going on there. And then I've got just a quick overview of the data set, and it goes out 55 columns wide and whatever. For this particular data set, the column 1 is meters of elevation where they took the sample, and column 2 is like meters distance to nearest water source. And the far right-hand column is the forest cover type is a number from 1 to 7. Those are the digits on the right there that say 55225, whatever it's going to be. That's like alpine forest or pine woods or meadow or marsh or whatever it's going to be. And then there's 50 other features floating around. It's a big pile of data. I'm going to run, because it's it's a forest cover type, I'm going to run random forest is a good thing here. So this is a machine learning algorithm. This is called random forest. I'm not going to go into a lot of details, but I'm going to build trees, decision trees, with random weaknesses. So I have a collection of 50 odd, here I'll just hit the go button here, take all the defaults. 50 odd sort of weak learners, where each learner is a decision tree, a cart tree, and then the sum of them, they vote together, does actually a really good job of finding and being able to run predictions on the data set. So if I run down here, no, it's not going to do this one's speed up. So I have to wait till this guy runs to the end. So we take like another 30 seconds here, and I'll have something done. So while we're waiting here, is it going to answer any questions about what this means or why you would care, what machine learning is doing here? Let's see, okay, so the general notion is this is predictive modeling. I'm going to build a model of the real world based on my input data set, with the hopes that the model will let me predict new things with sort of high degree of accuracy. So I'm going to get this guy a little bit longer here, and then we'll stop and take a look at him. So these predictive models are used by lots of people for different things, but for instance, it can predict whether or not this credit card transaction is fraud or not, whether or not I'm looking at some sort of DDoS attack, whether or not I'm looking at a blob of cancer on an X-ray or not. What is my estimated costs to insure the city of Chicago from the next hailstorm that comes through and is going to wreck some percentage of roofs in a neighborhood. What's the lifetime insurance costs of a particular population of people. There's all kinds of things you do with machine learning algorithms. And they can be very highly predictive. So let me explain this chart here real quick. Going down is the actual type of the observation made on the data set of what the person found when they did their ground truth. Going across is what the model predicts. So the diagonal is where the prediction was correct, and off diagonal is where the prediction was incorrect. So in about a minute here or less, I have a model that's about 90% accurate. So you can see about a 10% fail rate way over there on the right. Done on 500,000 observations in a few seconds on my laptop, and that's a reasonable result for not much work actually. If I was to have a cluster of machines, I could go a lot faster or a lot bigger or both. And I have a model that does something interesting. If I were to run random forest a little bit longer here, I'd get a more highly predictive model. And it's the general trade-off is some of the models we'll build are very fast to build with less predictive accuracy, and some are slower to build with more accuracy. Random forest is kind of in the middle. The other thing going on here is that some of the models are more interpretable. So yeah, here's my mean squared error by trees. It probably didn't have any other numbers in there. Yeah, it was built too fast. It's fine. So that's a unit you use to decide when to stop adding trees that you're not getting any better. Random forest is sort of in the middle of being interpretable. And what does interpretable mean? It means I can look at the model, understand why it's predicting what it predicts. Like logistic regression is very interpretable, although it's a weaker model, but you can read off the different coefficients on a generalized linear model, logistic regression, sort of directly understand why it's making predictions. And that actually turns into like government regulations. People do, say, FICO scorecard models. If you're getting credit allowed or denied in the US, you have to be told why you were denied credit. And so the government basically mandated you do logistic regression or variant thereof because you can explain the results of it to the end consumer that they got denied credit because of something. You go to the deep learning model, and it's highly opaque. You don't know why it predicts, but it's also by far the best predictor. Deep learning models are like these magical oracles that will, with extremely high accuracy, make all kinds of fun predictions.
These models, they're built in, or are they custom?
So this is the model I just built right now. It's sitting in the memory in my JVM. If I want to pull the model out and do something with it, I'm going to do something bad here. It's going to take a second or a few. I'm going to torture my browser. I'm going to pull the model out as a piece of Java code. So it's a straight up, plain old Pojo, but it's big enough that when I display it in the browser as a piece of code, it's a giant pile of text. The browser is going to barf here for a second. There it goes. Okay, so here is boilerplate we've all automatically generated, including instructions on how to compile it and how to use the model. But the goal here is to let you take this model and go into a production setting. So somewhere way down here after all the boilerplate, here's a tree. So I said it was a decision tree. Here's a decision tree. Float prediction is equal to, well, if you're missing, that's the NaN check. Else, if column 13 is, or column 14 is whatever, less than this and X and da-da-da-da-da-da-da-da, somewhere down here at the bottom, there's an answer. It comes out. Okay, it must have been, I'm going to pick 2 or 1 or whatever it's going to be. This is class 2 out of my 7 classes, right? So it's a decision tree. Here it rolls on, rolls on, rolls on. Okay, so the decision trees get big, and somewhere there's a second, and a third, and a fourth, and a fifth, and there's 50 decision trees all buried in here. And what it amounts to is if you run this code with a 90% accuracy, it will predict the correct forced cover type. And if I do the same thing for like credit card data, I'll have a model out that if I run with some level of accuracy, it'll tell me I got a fraud or not a fraud. This particular, all these models do no allocation in their core inner loops. They run sort of a finite fixed amount of code. So you can time them and know exactly how long they take. So if you have a time-sensitive scoring issue, like a credit card swipe, the guy's waiting at Starbucks for his answer, right? You have some number of milliseconds you're supposed to report, thumbs up, thumbs down at. You can count the number of milliseconds this guy runs at, and that's what it runs at. And it's just sort of ready to go in production right like that. So yeah, the model runs on and on and on. But it's all sort of straightforwardly stuff. If I do a logistic regression, the model's tiny. It's very, very simple. And you can see, all right, we can run a logistic regression here when we do that. Let's go, new tab, browser. So I'm doing this from the browser. There's a number of APIs we support. REST and JSON is an obvious one, and then the browser is built over the REST and JSON. Yeah, let's do that. Get a parse going. Okay. Yeah, come on. Done. So that was a much smaller data set. It's only 2 megs in RAM, 50,000 rows, 40,000 rows. Generalized linear modeling. We'll do generalized linear modeling. Okay, so here is an airline data set, a subfraction thereof. And the question is, can I predict whether or not my air flight will be delayed or not? This particular data set has a lot of what we call answer columns. So an answer column is something that you got after the fact. It's typically added onto data sets that's not available before you get on the airplane. So for instance, whether or not you're canceled in the middle here is only available until after you showed up at the airport and discovered the flight was canceled, right? So if you predict with that, the model will immediately discover that every time the flight was canceled, you were delayed. So it's kind of useless. So I'm going to exclude that. Except I just did the wrong thing here. Let's get rid of all of these. There we go. No, okay, fine. Let me try again here. It'll be easier to do it this way. If I do my shift click the correct way here, I'm looking for control click. That's what I'm looking for. There it goes. I don't want diverted or canceled. I do want distance and the origin and death. That makes sense. Clearly don't want arrival delays. CRS is the planned elapsed time. That I want to keep. Actual elapsed time I need to catch because if the actual elapsed time is really long, then somewhere I got delayed. I'm going to get rid of tail num and flight number because tail num is a unique identifier on most of the flights for this small of a data set. And it will simply predict if you got on a plane with this following tail number, your flight was delayed or not, because there's not enough flights for that one plane to have it not be able to tell otherwise. And again, get rid of the actuals and keep the plan times, and I'll just go for the time of the day of the week, the carrier, what time your flight was supposed to take off, your source and dest, and so on and so forth. Come down here, this is generalized linear modeling, covers lots of interesting cases, but binomial turns into logistic regression, which is a way to do true or false. I'm going to just take the defaults there. So logistic regression, I don't know if people want to go into how much math. Okay, we're done. So logistic regression is one of the ones that's actually pretty fast and scales very strongly so that you can get a logistic regression done on a terabyte in under a minute. It's a really fast model building. It has an easy to understand model, but it's less predictive. So here, instead of a 90% prediction, I'm getting around 70%, and you can see sort of the the red line represents a 50-50 die roll, and I'm better than 50-50, so I'm getting some predictive quality out, but not a huge amount. But on the other side, I can go up here and look and see what do these numbers mean, and what happens here is that the coefficients that are positive drive the equation above, the y equals 1 over 1 plus math, blah, 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 towards a 1. And the negative coefficients drive it toward a 0. And so is delayed being a 1 says the more likely that you are to be, the higher the coefficient, the more likely it is you're delayed. So taking off or arriving at this particular airport, I don't know what that is, or taking off from this other guy are both highly indicative of whether you're delayed or not. And if I run through here, there's Chicago, oops, here we go, Chicago Midway is right there. There's a few other ones that come up pretty quick that are kind of interesting. Destination, Austin, that's interesting. Okay, fine. I'll quit looking at it. But you can sort through and immediately start picking out, on the full-size data set, SFO shows up right away as like a bad airport to take off or land at. So does Atlanta. And then certain airlines like suck that you don't want to ever be on this airline, and other airlines are perfectly good. So you can get something out of a bigger data set here. This little data set doesn't have enough data to pick up all those features. But the equation is this. This is that is the model right there. So that's one line of Java code. You just drop that in your predictive or in your mobile phone app, and right away you get an answer out. Okay, so that's sort of the quick pass through the demo. Maybe I should stop and take questions on this before I flip back to slides. No, okay, fine. We're gonna go on here. Okay. So we've been very busy here, and the latest thing we're messing around with here is Spark integration. So we're doing big data stuff, and so Spark, although we have very different sort of models of data and execution, it's clear that there's an interesting integration going on here. We're able now to move data back and forth between Spark and H2O's data frames, and it's in process in memory, so it's actually pretty quick to go back and forth. And then you can take an H2O data frame and turn it into a Spark RDD and run Spark jobs on it sort of directly, like the one line of code you got there. And in addition, the H2O data frames now support a Scala collection notation, so you can just say for each and put some kind of map kind of code right in there. And the code's on GitHub. You need the dev version of H2O, and then Perrier is sparkling water. It's our combo. This will probably go away in another month or two. All we needed out of Spark was a hook to call H2O at startup time in the right places, in which we put a Jira request at the Spark people, and they've taken some version of it, and so it won't be too long before we don't actually need a Spark build. Okay, so we can move back and forth between the two, and it's all in memory, it's all in process, there's no external tooling needed. Mostly data doesn't move, it does change shape because it's going to be in Spark's format and H2O's format. And then there's a difference between eager and lazy, I'll cover in a second. And we do make a data copy, but the H2O data is typically very highly compressed over the Spark data, so that if you're running a successful Spark cluster right now, and you make a copy of the data, the extra memory you need isn't a whole lot over what you're already consuming for Spark. This is a little bit of the layout. Spark builds up from blocks they call partitions. These are structures that are limited to a single JVM. They don't cross a machine boundary. And H2O uses these chunks and collections for every column. You can have lots of these in any given Java heap, limited only by memory. And then, looking at it this way, an RDD is all of memory, all the data. An H2O data frame is all of it, but we're broken up by columns in the pink for the vectors, and RDDs are broken up by chunks. There'll be a couple chunks for every JVM. It's a little different format, but we'll go back and forth between the two different layouts with just a Java call to go hack the data around. When we convert the H2O data frames, the conversion happens immediately. It's essentially the same as a Spark checkpoint. You're going to run the, RDDs are typically lazy until you demand an output. H2O will demand an output, get its data in H2O format. Then you can do something with an H2O. All those things you do in H2O are all eagerly done on the spot. When you're done, you want to go back to Spark IDD, and you say, give me a tooo RDD. You get a wrapper object, so it's lazy at that point. But you've checkpointed in H2O, and then you can add RDDs all along. You'll build up your pipeline of computation, and when you ask for the Spark result, it'll pull the data out of H2O, convert in a Spark format, and then carry through the Spark pipeline, sort of the way Spark normally does things. Okay, so that's it. I'm just going to wrap up here. We have a couple different use cases people use the system for. So no distribution coding is basically whole algorithms or whole vector math kind of things. Often this is the REST and JSON style interface, and you're doing something like load a data set, run a logistic regression, get results, just what I demoed a minute ago. And you can drive this from R, Python, web-based, that was the browser you saw there, Bash, curl, scripting, however you want to run it. We do have an active R community who uses H2O as a way to get big data on R, and they can type their R expressions like they always have been doing in R, and the work's all done on the cluster on the cloud, and the data set sizes are 1,000-fold bigger than what they can do in R. You can dive under the hood and write code in MapReduce style. And that's pretty much good for any sort of dense linear algebra. Anytime I'm going to pass over all the data and do something. And passing over all the data and doing something is often on the order of modest millisecond counts. So it's fast enough. You can do interesting things with a bunch of passes. It's not the standard Hadoop MapReduce for speed. It's much, much faster. And then we support a bunch more complicated stuff I'm not going to talk about today. But there's a full-fledged key value store under the hood, and you can do kind of interesting graph algorithms and stuff with that. So in summary, most simple Java just works. We have map functions that go to the thousands and thousands of lines of Java code, and they all just work, and they look like Java code, and it runs like Java code, and it all feels right. It's fast. And everyone says fast, but we're running at the same speed as Java code would run on arrays, Java arrays. So it's as fast as you could get out of Java, which is pretty much CPU bound or memory bandwidth bound in most cases. It's as fast as the hardware is going to go. You can write big data as well, and it's a little bit slower, but not much because we're doing compression as you do writes. And like I said, we're typically memory bandwidth limited. We support the full Java memory model in a distributed cluster. There's no lazy consistency. It's all exact. And it's all actually fairly fast exact. Although if you do conflicting writes, you're going to follow the Java memory model, which will not necessarily give you the answer you want because it's pretty loosey-goosey about ordering. We can do transactional updates, which you do internally a lot for command and control kinds of things. And then we're writing, big data distributed analytics. Lots and lots of algorithms we've written. We're working on more. We're solidly working on 100 gig data sets. That's sort of the nightly Jenkins test. So actually each post-push test is now doing something on that order of magnitude. We're doing at terabyte scale stuff now. We definitely have customers using terabyte scale data right now. And we have paying customers in production, and it's all open source and free. So go download and play for big data. Yeah?
Questions. So you're working on these also these models, linear forest and
right.
forest, etc., on making more of those?
Yes. So the current, interesting new model coming out is Cox proportional hazards, which is used typically for survival analysis or lifetime analysis. Out of a collection of 1 million people in your insurance pool, some people die off at a steady rate after they've aged out enough. And while it may be harsh to think about people dying, it's what the insurance company does for a living for the last 100 years. And so they look at the large pool of people and they say, how many people are old, older, dead, and then, you know, we have insurance payouts, and what's the set of money and how much do we need to track based on the age of our pool, and that's Cox survival analysis. Same thing actually works for lifetime analysis of anything that you have and then it breaks and you don't. So iPhones, you know, what's the insurance coverage cost for the collection of people with iPhones on the planet when they die? And you drop it, and the screen broke. The longer you have it, the more likely it is that you drop and the screen breaks and you go in and get your insurance payout. So the guy who's doing those insurance run that kind of analysis on this, on your car, on I don't know. There's actually a lot of uses for that particular one. Yeah, and another question.
What happens if a node goes down?
So we're not an HA solution. So we looked hard at that, and we thought about it for a long time. And we know how to do it, but it's not worth the effort right now. So instead, we went for sort of raw speed, and most operations are all done with in seconds to minutes. And so if a node goes down, reboot the cluster. So the cluster will come up in seconds. Loading the data will take longer. It's whatever, you know, count of disks divided by max disk bandwidth. We can hit most disk drives to 80% of their rated throughput in a parallel data load, so without any trouble. And then you're up again. So if a node goes down, it's like a big calculator. And if a node goes down, you shut the calculator off, and you turn it back on again, and you go again. So it's in that sense, the deployment model is very simple and straightforward. If we get to the point where people are running jobs that take weeks, or a week, 2 weeks on clusters of 100 or more in size, we'll probably need an HA solution. And like I said, I know how to do it from a technology standpoint. Hasn't been worth to do it right yet. Yeah.
One from the queue is, any thoughts about running H2O on bare metal versus a VM?
Oh, any thoughts on H2O and bare metal versus VM? Yeah, so this is sort of the obvious story about VMs versus H2O. We've been looking at that actually right now. A lot of people. Usually VMs add some amount of overhead. H2O will burn all your cores and all your memory sort of easily. And so if you add overhead, you just slow yourself down. It's not like it makes sense to have it share nicely with somebody else on a neighbor, because H2O is not actually a nice neighbor. I mean, when you say go, it's going to take everything and go. And so it doesn't work well. It's not that it doesn't work at all. You can work fine. It's not a nice neighbor for having, you know, being on the same hardware. We do test and we run that way all the time. It's because it happens, you know, people do it that way. But it's perhaps not the best way to set up a cluster for running H2O. That said, we run an EC2 all the time. That's a very standard setup for us, and those are all obviously virtualized.
You mentioned Hadoop and HDFS on the way. What was the connection?
Yeah, okay, so it's complicated. There's essentially no connection, but it looks like there's a really big connection. So the connection is most people's big data is in Hadoop, HDFS. So we'll read from HDFS as a parallel file source just fine. We'll read from S3, we'll read from local drive, we'll read from all these sources, including HDFS. But we don't need to be on a Hadoop cluster. But we can. So we'll play nicely in the Hadoop ecosystem as a funny kind of a mapper job if you want to run us on Hadoop, where the map sticks around forever, it never goes away, and then, you know, burns all cores when it goes and is idle when you're not running it. So it's a kind of a weird mapper job. It's not very efficient in that sense, but it's not too bad. And what really happens is we go into somebody who's interested, you know, in putting H2O in production, and they already have a big Hadoop cluster lying around, but they don't have a spare bare metal cluster lying around. So we'll run on their Hadoop cluster because that's the quickest way to get a cluster operation going. Now that said, most Hadoop clusters have machines that are spindle heavy and CPU and memory light, and we exactly want the CPU and memory. And so you get a giant collection of tiny machines, and that's sort of not necessarily the optimal way to run H2O. So you're frequently better off with fewer, fatter nodes. Is it going to come back? But not that it says anything there. So you know, along the line of fewer, fatter nodes, what a configuration for a machine looks like that is sort of interesting or works well or doesn't varies by what you want to do with it. The logistic regression is strongly scaling, and so you really can get away with a large sea of smaller machines, and it will do great. Random forest typically has more network bandwidth, and as the trees get deeper, you have to build these histograms. They get exponentially bigger as the tree gets deeper, and suddenly you have very large data sets that are getting slopped around between nodes. And so your network throughput becomes an interesting bottleneck, and you're better off with fewer nodes simply because there's less network traffic. You go to deep learning, the deep learning runs, or neural nets, runs these neural net algorithms that within a node are extremely efficient using this hog wild algorithm. They're racy and like sort of crazy fast. But the models all drift from each other independently because there's no x86 coherency hardware across a node. And so that has to be taken care of by shipping the models across the wire to resync them back up, or they drift too far from each other. When you resync them, they sort of cancel each other out. So you want to keep resyncing them. And that turns into a network latency as opposed to bandwidth issue. So some of the algorithms are sort of network tolerant and some are less network tolerant. And so you kind of varies by algorithm whether you want to have whether you can get away with fatter nodes or skinnier nodes and more of them, or fatter nodes and fewer of them. All right, well, that's actually, it's about time, and I'm done with slides. I have a lot of little fun extra add-on slides I can go through if people want, but why don't we call this the official end, and I'll be around for a little while for Q&A here.